Okay. Morning, and start the lecture. So we're moving on to the concept of a common filter. Okay. So common filter deal with is basically a situation when system is is interfered with a certain amount of noise. So what we need to do is we need to have some quick reviews on some probability and statistical concepts. Okay. The electoral students have, I think all of you, right, should have taken the probability course. Mechanical students, you taking 254, the instrumentation and data analysis. Yeah. So we had some probability and statistical concept in that course too. So the only catch is in 254, the statistical concept in that is univariate, basically it's a single variable. So what we're dealing with here is actually it's a multivariable basically situation. Okay. So I just want to cover some of the concepts that's needed for the common filter. All right. Yeah. Okay. So first of all, okay, random variable. Okay. If we have a random variable x, okay, and some of the quantity that we use, we know is what's the mean, basically what's expected value of the random variable, right? So mean meaning expected value. So E representing this one here, and the formula is infinite negative x, f of x, and dx. So this is for continuous, right? F of x here is the probability density function, or something called a probability distribution function. Okay, so it can be all different kind of distribution function. So for example, it can be uniform distribution function, it can be a Gaussian distribution function, or some other functions, right? Yeah. If it's a discrete one there, so the way that we write this, sometimes we write just mu and then the capital X set it here to indicate that's the expected value for random variable x. If it's a discrete one, so sigma, and x and f of x, and the small x belong to a set, okay, s of x, basically that's the set, okay, of all the real numbers, okay, yeah. So, and this is for discrete one here. So these are expected value. And this is a statistical equation here. Okay, so now we also have a variance. Okay, so if we were talking about variance here, so we use this VAR, okay, X, capital X, that's sigma, capital X squared, right? That's variance. And that equal to capital E, capital X minus mu, okay, square at here. Okay. And in terms of formula, because E, expected value of X is this, then expected value of X minus mu square is X minus mu square f of X dx. So that's variance. So variance basically, it's okay. You're looking at it's a sum of the difference between the value is the square of the x minus the mean value, mu. Okay. This is for continuous. If it's a discrete, right, then its variance, the x, is going to be sigma x squared. That's the same thing, equal, okay, the total here, total sum, x minus mu squared f of x here. Okay. And x belongs to a certain set, okay, certain outcomes. It's a set of all the outcomes. Okay, so that's the variance of a this is a variance, right, for a single variable here. Okay. And there's a little extension in this formula. It might be useful here for some of the future proof at here. So basically, sigma squared, let's just use this, equal to E x minus capital X minus mu squared here. So what does this equal to? So you can expand the term in the inside the bracket. That's x squared minus 2 mu capital X and then plus mu squared. Okay, plus mu squared. Technically, I should put a subscript capital X under the mu. That's okay. So E of this and that equal to E capital X squared minus mu is a constant, so you can take the mu out of this bracket here, and E capital X plus E of mu squared. Expected value of a constant is itself, so that's basically just mu squared. Okay, yeah. And expected value of x, and that's basically mu, right? So 2 mu squared negative plus 1 positive mu squared, so the whole thing equal to expected value capital X squared minus mu squared. Okay, yeah. So that's the relationship between sigma squared and mu squared at here. Okay. Yeah. As we learn later, this term at here, okay, we're going to define. This is called an auto correlation at here. Okay, it's called autocorrelation. Okay, so this is a single variable here. Okay. Or univariate, as they call it. Okay. Now, if we have let's say two variables or multivariable situation, then what we need to know is the concept is called joint, okay, probability. Okay, joint probability here. So if we're dealing with an x and a y, basically x and the y, okay, two random variables. Okay, two random variables. So basically the question here is, so what's the chance, for example, for x and y to occur at the same time, right? That's basically the situation here. Yeah. So what we need is so-called joint probability. Okay, this density function. So this is basically f of we use this f of x y, then x y at here. Okay, f of x y and x y here. So this is the joint probability, okay, density function. Okay, so and this one we didn't cover in 254, but lecture students should learn this already. And there is a chance, okay, there is a formula that you can derive, okay, based on this joint probability density function to get the probability distribution function for f of x and f of y only, right? So that's what we call marginal one there. So f capital X, okay, of x equal to this. Okay, positive and infinite, f x y capital small x y, and then dy. Okay, so this is how you can get this f capital X of x and y and dx right here. Okay, Now there's one very important concept basically. X and Y, okay, they are probably independent. So if X and Y, okay, are independent, so this is a very important concept. Okay, so what does that mean? Basically, if X and Y are independent, meaning the occurrence of X or the occurrence of Y, okay, does not affect the occurrence of the other one, basically. All right? Yeah. So if this is the situation, then the f capital X, X, Y will equal basically this and multiplied by this. Okay, equal this multiplied by this. Okay, so that's the independence. Now, in terms of the expected value, let's say if I have an expected value of X and a Y here. So what's the expected value of X multiplied by Y? Now, if they are independent, then this just equals expected value of X by expected value of Y. Okay? Yeah. So the kind of a process that we're going to deal with will be imposed by certain amount of noise, and the noise we're going to consider the Y noise, and that's actually what we're going to consider as independent. Okay, yeah, for a different variable, there are different Y noise. Okay, and this is the kind of a quantity we're going to look at it shortly. Right? Yeah. So that's the probability, joint probability. There are some other, basically what's the distribution, what's the cumulative function, and some other things. But the one I think I want to cover here is called covariance at here. Okay. So what can I label it here? Joint probability covariance. So variance for single variable, this is a variance, right? This is a variance at here. Okay, this is variance. Now, because it's two variables at here, so we're dealing with so-called covariance at here. So covariance of this X and Y. So what do we use? We use COV X, Y at here, okay, to indicate the covariance. Okay. And that equal to this. So E, okay, X minus mu X, Y minus mu Y. Okay, so this is the covariance. So covariance basically it's a quantity, it's a value tells you how does X and Y, what's the trend, the change of X and Y between X and Y. Do they sort of always change in one direction? You see what I'm saying, right? So is X always changing positive? If X is changing positive, then Y is also kind of a changing positive. So basically, it gives you a sense of the relationship between X and Y here, right? Yeah. So let's say X and Y are in a kind of a linear relationship. So let's say maybe Y equal to kx plus b, right? That's a straight line. And then with a certain amount of noise added here, okay? So X and Y are in a linear relationship, then you'll see that the covariance XY here will tell you that kind of a trend there, right? Yeah. So if you expand, okay, what's inside the bracket here? So that's XY here, and then minus the X by that. Minus mu X by Y minus mu X mu Y. Okay, yeah, expanded. There's two here. Now let's make a little assumption in here. Let's say X and Y, okay, are independent. Okay, but however, we don't need to do that. But let's look at this one here. If I expand this one here, what do I have? I have expected value of X, Y at here. Expected value of this, expected of this, and expected value of this, right? Yeah. expected value, this is a constant, this is constant, so this you can take it out of bracket. Expected of x is mu x, expected of y is mu y. So there is a mu x, mu y, mu x, mu y. There are two things, right? And this is plus, right? Yeah.
Is that like a subscript 1 or? Like
no, y here.
No, but it goes x something.
Oh, mu. That's how I write the mu here.
Oh, okay, perfect.
Yeah. Because otherwise it's u, right?
Yeah, for
yeah.
Sure.
I think more proper maybe just, I don't know.
Okay.
Yeah. Okay. So overall this equal to minus mu x, and here it comes again, yeah, mu x and mu y. Yeah. Okay. So if x and y are independent, okay, if x and y are independent. What is independent again? Because it basically means they don't rely on each other, right? They don't. The occurrence of one doesn't affect the occurrence of the other. So, based on the meaning of the covariance, covariance tells you what? The relationship between the two random variables. So technically, if they're independent, so they don't have any relationship, then the covariance is supposed to be 0. So does that make sense? So E of x, y here, independent. Remember I said if they're independent, this Ex, Ey, right? So Ex, Ey, mu x, mu y minus mu. So that basically means covariance of x, y equal to 0. All right, equal to 0 here. And then some other property here is if you replace the y with x, well, what do we get? Variance, exactly right. You put x, that's basically the variance of this random variable x here, right? And based on this, covariance formula here, so this quantity here, we define it as so-called correlation. So correlation, we call it Rxy equal to that Exy here, okay, Exy. Okay. And there's one more very important, just based on this one here, is called correlation coefficient. So essentially, it's a normalized covariance. Correlation coefficient, and that's defined as rho capital X capital Y equal to the covariance capital X capital Y divided by sigma X sigma Y. Okay, like this. So this is a little bit, you got to be a little bit careful about the names that are here, okay, but the name sometimes is a little bit confusing, basically. Correlation, so that kind of probably tells the correlation of x, y. Actually, this is a covariance, okay, as this quantity tells you the relationship between x and y, okay? And the correlation coefficient is a normalized, you see, right? Normalized by what? Basically, the covariance normalized by the value of sigma x multiplied by sigma y, right? Yeah. So this quantity rho xy normalized basically means the value rho xy will vary between -1 and +1 value here, right? Yeah. So if x and y are independent, so as you can see, the rho xy must be equal to 0. And if x and y, let's say if x and y are in a linear relationship, let's see, equal to kx. Okay? Yeah, that's a capital X. Then k could be a +1 or -1 here. So that rho xy will equal to positive, negative 1. Okay, yeah, normalize the row there. So independent, okay, so there's another thing is independence, okay, if two variables are independent, then it means, okay, they are not correlated, right? They are uncorrelated. Okay. However, if two random variables are uncorrelated, that doesn't mean they are independent. Okay, there's this fact here. Okay. So they are not necessarily, okay, independent. Okay. But if both of the random variables are Gaussian, okay, and unrelated, then they must be independent. Okay. Okay. Yeah. So this is some of the connection in here, right? Yeah. Okay. Yeah. So to extend the situation a little bit further here, okay. This is just two random variables here, right? Just two random variables. Now, how about here? If we have so-called a random vector at here. Okay, a random vector. So what does the random vector means here? It basically means we have vector at here, and then we have a series of random variables, x1, x2, up to xn. So those are capitals. Okay, so we always use column as vector here. This is called a random vector. Okay, so as a vector contains, okay, n number of random variables here. Okay. So we can define another one. Let's say define a y at here. Okay, let's see. Okay, so this is useful because later I will show you here. Basically, we're gonna have our system, for example, g of x of k here plus hu of k, right? So this is our original discrete system, right? So now the system at here, okay, will be contaminated by certain process noise. So the process noise is going to be indicated using w vector of k at here. Okay, yeah. So w, let's say you have n number of states, then the w has w1 up to wn, right? So that's a random vector there. Okay. Yeah. All right. So now let's take a look at a couple of things here. How do I make use of some of the concept we just reviewed here on the random vector? So first of all, expected value of, okay, of this x would be what? Would be e x. Okay, basically expected value of this whole chunk at here and that's equal to expected value of x1 at here, and up to expected value of xn at here. And that's another vector here. Okay, vector. Okay. So when we have two variables and we have this concept of a covariance, okay, we have the correlation, okay, like this. Yeah. So more technically, let's say this two variables, you can call it a cross covariance, basically, because there are two variables here, right? But if it's just a two, we can just call it covariance, all right? And same thing here. If this is just covariance XX, we can call it autocovariance here, okay? But it's just one random variable, so you can just call that covariant. Now we have a random vector here, and if we try to compare the relationship between x vector and y vector, right? So now we have this concept called, let's see what's called the covariance, called cross covariance now. Okay, x and y. Okay, x and y. So what does that equal to? That's covariance x at here, y at here. Okay, covariance x at here, y at here. So we use c x y, okay, so to indicate this this symbol right here. So that equal to e, okay, x, okay, minus mu x bar, mu x vector, okay, then times y minus mu y transpose. Okay, transpose that here. Okay, so first, before we move on here, just look at the formality, right? Because sometimes when you move on from scalar to vector, essentially it's still the same thing, but the read to write it is just slightly different now, right? So when you have single variables here, when you have just one scalar here, x and y, the covariance is ex this, right? Yeah. So when they have vector here, yeah, we didn't change much, but we just changed the symbol to vector here. But then we added a transpose at here, right? A transpose here. Okay, yeah. So what does that mean? Basically, you need to think this x is it's a size of how much this is what? N by 1, right? It's N by 1 here. And what's this one here? When you transpose that, becomes 1 by n. So n by 1 times 1 by n. So this whole chunk is actually an n by n. So the covariance coming out of here is actually a matrix of n by n at here, right? So technically, we should call this is a covariance matrix at here. Okay, this is a covariance matrix. Okay, covariance matrix. So if I expand this chunk at here, what does that look like? Okay, if I expand this one here, then that's E. It's a matrix. Okay, it's a matrix at here. So the first element at here is just expand, just basically replace all those things with the vector x1, x2 and to n and y1, y2 to yn. So that's going to be x1 at here, mu x1 at here times y1 at here minus mu y1 at here, right? Yeah. And then keep going up to where? x1, mu x1, and then yn, mu yn, right? Yeah. So finish the bracket there. Okay. That's the first row, right? That's the first row. And then this up to the last row, that'll be xn, mu xn, y1, mu y1, and up to xn mu x n yn mu yn. All right. So that's the cross covariance. That's the covariance matrix between x and y. Okay. In a very short expression, and this guy here, basically, if you don't want to expand it, if you use a very short expression here, and just like this guy here, right? Just like this. So what do we do? We just change this x to x here, y. That'll be y transpose out of here, right? And this is going to be mu x and then mu y and transpose like this. All right? Yeah. So, and maybe I'll just write here. This is mu x, right? This is mu x is expected value of this. So that basically is the same thing as expected value of x, y minus expected value of y transpose out of here minus mu x and mu y and transpose. Okay, it's equivalent in terms of writing of this. Okay, that's covariance. So what does the covariance do? Basically, if you look at the elements, right? The elements of each one of the matrices that are here, that basically tell you what information does that tell you? For example, this one here tells you the information what? The relationship between x1 and y1, right? Yeah, and relationship action. So basically, it tells you all the relationship. And the other thing is, what's the nature of the matrix here? You see this quantity here and this quantity here. They are what? The same thing, right? Are they the same thing? Oh no, they are not the same thing. Not this one here. No, yeah, they're not the same thing here. You know, I'm looking at here. No, not the same thing. Now the next ones will be the same thing. So now I'm going to change the y, okay, to x here. So basically, if you change the y to x, okay, so that's now what we call it, the auto covariance now, right? The auto covariance, right? Yeah. Auto covariance. So in terms of the matrix expression here, okay, so let's use a cxx out of here, or just one single x, sometimes just if it's an auto one there, okay, and that equal to e x minus x minus mu x x minus mu x again transpose. All right. Then this matrix set here, right? This matrix here, you just have to replace all the y's with all the x, right? With all the x. Okay. So bear with me. Maybe just write a few one here. Well, the first one is x1 minus mu x1, this multiple this. So this is basically squared, right? It's basically squared here. Okay, it's basically squared. And up to x1, mu x1, xn, mu xn. And here is xn, mu xn, x1. That's what going here. Yeah, x1, mu x1, and up to xn mu xn squared. Okay, so that's the matrix right here. So now you look at this matrix, the autocovariance matrix right here, and then what happens is this quantity are the same thing, right? So basically what it means is this matrix is a what? What kind of matrix is this autocovariance matrix? So basically this whole chunk is the same as this whole chunk. What do we call this matrix? Symmetric matrix, right? Yeah. What's going on here? You're not graduating yet. So this is a symmetric matrix. Okay? Yeah. Okay, so then you look at the diagonal elements here. Okay, look at the diagonal elements. So what are they? This is x1 mu x1 up to xn mu xn. So basically, expect this is basically what the if I write it down to the matrix here. So what would I got for this matrix? So this first element is corresponding to expected value of this, which is what? Which is variance sigma x1 squared, right? And then up to where? Sigma xn squared. Okay. And then the other elements, right? The other elements here. Okay. Yeah, that's not sig, but we can write that as kind of basically this is kind of covariance basically, right? So where is that? That's basically single variance. The notation of single variables like this. That's basically in terms of this kind of formality here, right? Yeah. Okay. Yeah. So let's also use something like here. Okay. Yeah. So now, okay, let's think about the special situation. If you look at this random variable here, if x1, x2, and xn, they are all independent of each other. Okay, they're all independent of each other. Exactly. So which means the covariance of any pair of them will be 0. So which means what? Those alpha diagonal elements here, they will be 0. So then that's the next very important writing in here. That's what we're going to use actually. Okay. If xi are the xi's are independent, then this Cx matrix out here becomes just sigma x1 squared 0, 0, 0, 0, sigma x2 squared and up to sigma xn squared, right? And 0 right here, like this. Okay. Okay. Yeah. Okay. Yeah, I think there's another thing that we are also got to be clear is this. Just thought of that. What does a variance mean, right? What does mean and variance basically means here? So let's see if I have a Gaussian distribution. What's the center value again? Mean, right? And then this one here, so probably it's the variance of sigma standard deviation. Yeah. So if I have another one with the same mean but a smaller variance, then the distribution will look like what? Yeah, right? Like this, right? Yeah. So I think you probably will prefer this one in the statistical point of view than this guy here, right? Yeah. Okay. So when we design a common filter, okay, just remember this concept here, okay, and in that particular case, a common filter is going to also be an optimal kind of a sense. Okay, you're going to minimize something, but okay, in that case, you're going to minimize is trying to minimize the variance. Okay, so trying to minimize the variance set here. Okay, yes, but you're trying to get a smaller, okay, a distribution like a variance, just a distribution with a smaller variance set here. Okay, and not just minimize just one. You're actually going to be trying to minimize a covariance matrix. Okay, you're going to be matrix there. All right, so a couple more concepts here is this. So let's see, looking at here, okay? So look at this one here. Look at this one here. Now remember, what do we define here? We defined this guy here. We call that what? Correlation, right? Define a correlation. So I can actually define the same thing. If it's a vector, I can define this guy here as our correlation at here, right? Yeah. So this is, let's say first this cross correlation. So we define as R, X, Y at here, and that equal to expected value of X by Y transpose. Okay, it's value Y transpose. It's a vector, right? It's a vector. And same thing. And this one, what is this one? Is X is 1 by n, this is n by 1, so this is n by n, so this is another n by n matrix, right? N by n matrix. So if you write it out, it's expected value. You can write the E into the matrix, okay? Or you can write it outside matrix, that's fine, okay? So x1, y1, okay, up to, okay, this is x1, yn, like this, okay, xn, y1, xn, yn, right? So that's the cross correlation, cross correlation. Now, what about the autocorrelation? Okay, the autocorrelation in here. So for the autocorrelation, it's Rxx, Rxx, and expected value of x right here. Okay. Yeah, transpose. So let's change that x1, just change the y with xx here, right? Okay. Now let's take a look at observation in here. Okay. Yeah. What's the connection between this autocorrelate correlation and this the autocovariance matrix here, right? Yeah. So we said if X vector contains random variables, where they are all independent, then you have, okay, a symmetrical matrix of this one here, right? Yeah. Now let's add on one more condition at here, okay? So let's say if xi's, okay, are independent and zero mean. If they are independent and zero mean at here, okay, then if you look at this autocorrelation at here together with this guy here, so basically maybe just look at let's see, which one? Maybe just let's see here. Where is that? This guy here. I don't have a quote. Well, anyways, we can just take a look at this one here. So basically, if there's zero mean, basically means what? This is 0, this is 0 here, right? And if they all zero mean, it basically means this is 0, this is 0 here, right? So then this guy here basically the same as what? As this guy here, right? And this guy here. So the covariance will become the same as the relationship, right? The correlation at here, okay? The correlation. So this matrix, basically this matrix at here, okay? If they're independent zero mean, so that matrix, the R, the XX here, will become the same as, not a vector, will become the same as that's called the auto covariance matrix here, right? Same as that. Yeah. As a matter of fact, if you look at this from statistics speaking, now because variance here, they're all positive numbers, right? Those basically squares, so they're all positive numbers here. And if they're all positive numbers, they are basically a diagonal matrix. So this is what we call a positive semi-definite, because maybe it could be zero, right? It could be zero. So this is called positive semi-definite matrix here. Okay. So those are the fundamental concept here relates to what we're going to cover. We're going to use in terms of a system here, right? Yeah. Now there's one more very neat property. Okay, we may need or may not need here, but I'll just write it here. If we have y equal to ax plus b, so the random vector y is in the linear relationship as the random vector x, right? Yeah. Then if I wanted to know what is the distribution of the y, right? Let's say we have the x set here, okay? So basically for x, okay, what we write is x belong to a distribution, let's say a mu x and a cx. Okay, so basically x has an expected value, mean value of this, and x has a autocovariance matrix of cx, right? With single variable, is basically it's mean of that and the variance of that, right? Yeah. Then if y is in this relationship here, then the y, I can use n here as an indicator distribution. The y will be in this. Y will be this. Okay, the property is this. Y will be n. Okay, so a mu x, okay, plus b. This is a vector here. Okay, so a mu x plus b. So a, b are scalar value, right? So the mean value of the y didn't change much, just scaled up by the matrix A and vector B. But the covariance matrix, okay, for the y, okay, will be changed, and that's actually called. So if I write it down here, you'll see this. So it's A cx here and say A transpose. So that's kind of a linear transformation. Very much looks like a similarity transformation, right? Yeah. So if you have the x now, you don't have to compute y. You can just simply use this relationship here, okay, to obtain the y's mean and the y's covariance matrix, right? Yeah. Okay, so here's a little simulation. You should check it out from the lecture notes here. Okay. So in MATLAB, let's say if I wanted to generate, okay, a white Gaussian noise. Okay, so basically, let's say xi, right? One of the random variable is so-called white. G. How do you speak? Did I spell right? G. If this is this one here, so y Gaussian noise meaning it's a zero mean and a certain variance there, right? Yeah. Now let's say if this is one symbol here. If xi is not just a white Gaussian, maybe it has a certain normal distribution, but it has certain kind of a mean value here. Okay, if I understand. So there are two ways of generating the noise here. So how do we generate? If I use MATLAB, how do I generate this kind of noise here? So what do we do is we can use this MATLAB command called RANDN. Okay, yeah. So RADN it's a function to generate normal distributed, okay, basically normally distributed numbers. Okay. So what you do is you give it, okay, a certain kind of a number L. Okay. We generate just L by 1 or 1 by L, doesn't matter. So L is a number. Okay, L is a number. So L, the higher number of L is, then the overall it'll be more and more look like what you're looking for here, normal distribution, right? Yeah. So let's say if I wanted this general case here, okay, if I generate here, so I wanted random variable has a mean of a certain value, has a variance of this value here. So what do? You use this. Basically, your xi, okay, equal, okay, mu xi here times this RADNL1 and plus sigma. That's right. What's going on here? Sigma here and mu here. Okay? Yeah. So you can use this way to generate the noise as you want. All right? Yeah. So if you take a look at the code here, so I'm trying to generate two sequences here. Okay. One is S, one is R. I'll define it the standard deviation and mean here. So you can use this to generate the noise as you want here, right? Yeah. Give a certain key here, and you can plot and take a look at what does it look like? Okay, what does it look like? So the point here is, right? You have X and you have this. Let's see here. You have this S and R, right? You have the S and R here. Now, if I construct myself a Z vector, which is SR like this, okay? If I construct a vector, so S is a random variable, and R is a random variable, right? Yeah. So this is basically a random vector now, right? It's a random vector. So we can basically try to verify a couple of the definitions that we have just defined it here, right? Yeah. What will be the autocovariance? Okay. So I'm supposed to get what? To get this, right? To get this. Okay. So if I want to generate the autocovariance, so what do I get here? So basically I wanted to see what's a CZ, right? What's a CZ? So I'm supposed to get what? Sigma S squared here, 0 here, 0 here, another 0. Well, yeah. Second here, what do I get? Not necessarily 0, right? Yeah. Not necessarily 0. Yeah, it's got to be 0 because the way we generate S and R are independent. Okay, it's going to be 0. But if I write it in general, it will be basically it will be what? It will be S minus mu S and R minus mu R, right? Yeah. So technically, in general it shouldn't be 0 here, but in this case here, the way we generate S, because we use RNDA, so S and R are independent. So S, R are independent. Okay, so we should get a 0 and a 0 here, and the variance of S and variance of R at here. Okay, so that's the technically what we should get. So what you can use is you can use a MATLAB command called COV. Okay. You can use a MATLAB command COV here to verify the theory. But you probably will get is this. You see, we're going to get is the matrix out of the MATLAB. We're going to get a matrix like this one here, right? So the elements that are here. So my S has a standard deviation of 3. The R has a standard deviation of 6, so I should get 9 at here and it's 36 at here, right? Yeah. But you don't get exactly 9 or 36. The reason is because our length of the noise is not infinite, right? It's not infinite. It's only a limited number of 10,000. 10,000 here. It's 100,000 in here, right? 100,000. Okay. So if you have a supercomputer, you can punch in a ridiculous high number with all the memories that you require. You'll see this is going to be getting very, very, very close to 9 and 36 here, right? Yeah. Okay. So that's how you can vary here. Okay. Okay. So back to the lecture here. Okay. Now coming to exactly the point I wanted to make now is this. So the point here is we're dealing with, okay, so the concept is called stochastic process. Stochastic process. So the challenge is usually you need basically a whole term, of course, to deal with all the situation here. But just make sure you're focused here, okay? It's not purely on the statistics and probability things here. It's a little bit just we know what's going on here, and we're going to use that for our computer design there, okay? And in the end, more important is you're able to implement that on the actual system, okay, in real-time control, okay? Yeah. So what is a stochastic process here? So let's say we have a so-called a stochastic process. So I'll use x of t. So I'll use a continuous one. For example, right here, I have a process x of t here. So here's what happens. So you have you give initial condition, so t equal to 0. Okay, t equal to 0 here. So let's say you purposely, okay, use the same initial condition. Okay, same initial condition every time. That you can do. Okay, so you use the same initial condition for this process that is here. So what's the process? You know, any system. You know, any system when you're talking with when you're looking at the operation of nature. So those are process basically, right? So if you give an initial condition at here, and you'll see that then you ran it. You ran the process. So let's say this is your trial number 1. Okay, if your trial number 1. So then you try to observe the evolution of the process here. So you'll see that it's, you know, basically noisy things like this, right? Yeah. Okay. Now, if you have a second trial, okay, you can look at a second trial here. Same initial condition. Okay. So let's say if I have a process has no noise, right? No noise, it's clean. Then technically speaking, if the same initial condition and nothing else but just change, no change at all, no system parameter, no change, and then initial condition, no change, then the time history or the evolution of the process or the response, this should be what? The same, right? It should be the same. But because now you have noise in the system, we call later sort of a disturbance in here. So the change of the process is not going to be the same as this one anymore, right? So it's going to be a different one here. Okay, just draw random here. Okay, yeah. So if you keep going, you run as much as possible. You know, the number n trial. Okay. So each time you have the same initial condition. Okay. And they all generate a different response, right? Different response. Is that good? Yeah. So basically, okay, and the second observation is this. If I particularly taking just one time moment, okay, if I look at basically, okay, all the trials that I have conducted here. Then I look at just one particular moment. Let's say call it T1 and here, and maybe look another one here, and maybe this is T2 and here. Okay, T2 here. Okay, so then at this moment, trial number 1, you have certain value at here, right? Trial number 2, you have the certain value here, and trial number n, you have a certain value over here, right? So basically, for the instant or time instant t1, what do you have? You have like a sequence of a number here, right? You have sequence number, and that sequence number we call that basically x of t1. Okay, x of t1. So if you're just interested in the x of t1, that is one random variable, right? That's one random variable. It changes, right? Every time it changes. So this x of t1 or x of t2, okay, they are basically random variables. Okay, random variables here. And if they're random variables, then technically speaking, there should be a probability density function, right, associated with that random variable. And same thing, there should be a probability density function associated with that random variables. And if this is random variables here, if you add all the points up divided by the total number, you get what? You get a mean value, right? So at each instant, right, at each instant, you get a mean value. So you will have a mean value for that instant. You will have a mean value for this instant. Okay, depends on what you take. Okay, and if you compare these two instants, you want to see, is there any connection between, is there any relationship between the two time instant t1 and t2? So what we can do? We can look at the covariance, right, of these two random variables here. Okay, or we can look at that correlation, okay, of these two random variables here, okay, of the correlation. Now, essentially, the stochastic process, basically, you look at this one here, right? It's a process. You can write it as, so x of t, you can write it as x. Okay, you can write it as what? You can write it as a small x, t, and s. Okay, small s, t, s. It's a sort of it's a space and a time system. It's a space and a time system. So t represent basically the evolution of the time, and s represent the number of trials that you conducted here. Okay, so for each trial you have one time history. Another trial you have another time history. Does that make sense? Yeah. So that's a stochastic process here. Okay. As a matter of fact, if you take all the points right here, then you trying to get the average of this one here. There's a name for this. This is called what? This is called ensemble average. Okay, called ensemble average. Did you learn stochastic process in 460? Right? Was it 460? No. Yeah. No. Okay, so coming back to this stochastic process now let's think about the special case. Okay, think about a special case here. So as we said, at a different instant, okay, at each instant you have a mean value, you have a distribution basically, right? You have a variance. Okay. So what if the xt1 and xt2, or basically what if the random variables representing at a different time instant, they are independent? Okay. So if this fx1 of t for the x, okay, not this one, if x of ti, okay, are independent. Okay, if they're independent here. I should see the other, but anyway. So if they are independent, and it happens that the distribution of this, basically at each one of the instances here, they all have the same kind of a distribution. They all have the same kind of probability density here. So let's say at this location here, maybe it's a Gaussian distribution. Okay? And here is also a Gaussian distribution. At each location, okay, at each location, it's all Gaussian distribution here. Okay? Yeah. So that's the clear, and all have the same, okay, probability distribution or density function. Okay, so it essentially means what? F of x t1, okay, equal to f of x of t2, and you know, whichever you want. Okay, basically. So all have the same thing. So we what's going on? So no hurry. Subscript, right? We use subscript. F distribution, f of t1 for the x here, f t2 for the x. So they all have the same, okay, probability distribution here. Okay. Now, if this is the case, then this stochastic process is called stationary stochastic process. So give us the so-called stationary stochastic process. So basically means the statistic characteristic, the concept doesn't change as the time goes on here. Okay, so this process everywhere has the same kind of statistics. So that's a stochastic process here. Okay. Yeah. Yeah. When I actually graduated from master degree, before I move on to the PhD, and so I was having an interview at an ENGR487, and so the guy asked me a question: can you tell me what's the concept of stationary process? And I was having no idea, so I said something which of course totally doesn't make any sense. So what's the stationary stochastic process? This should be your answer here, right? Yeah. Okay, so now let's come to a white noise. Okay, let's talk about white noise here. Okay, talk about white noise. Okay. So white noise, let's use this symbol here. So I have a sequence of numbers. Okay, I use a sequence, this W of n. So what do I have? I have a W of 0 here, W1 here, and W of n here. Okay, like this. So you can use MATLAB. You know, think about the process here, right? You can use MATLAB to generate a sequence white noise. You know that 0 mean basically, and a certain variance. Okay. Now, if you try once, so run the MATLAB the RADN, right? And with a certain sequence, with a certain length. So you run it, you generate one length, right? You run another time. What would you expect? Would you expect the same thing gonna happen, right? No, Actually, you can, right? You can use the so-called the random seed to ensure that the second time is the same thing. But just in general, the second one will be different. Basically, the second trial for the same location and here, it'll be different, right? Same thing here and here. That makes sense? So basically, if I keep doing this, if I keep doing for any number of times here, so what do I get? So each one of the location and here is what? Is a random. I can call this is basically a random variable here, right? And this is a random variable, and this is a random variable. That makes sense, right? So the white noise is basically a stochastic process at here. The way you generate this white noise at here, it's a stochastic process, right? And guess what? What's the mean if you look at the n number of trials that you ran, and then you look at for the 0 location, 1 location, and n location in here. What's the mean value here? Yeah. What's the mean value here? Each location has what? Has the same distribution, right? Will have the same distribution. So the white noise is basically it's a stationary stochastic process. Okay, stationary stochastic process. So. Okay, it's a stationary. And our noise that's going to be added to our system is going to be this white noise. We consider as white noise, and it's going to be stationary. Now, what's so particular about the white noise? Now, you probably learned this in the 460. If you look at the spectrum of the white noise, what do you see?
So flat.
It's flat, right? Yeah. Okay. Yeah. So now, you probably question is, oh, white noise, do you have a color noise? Yes, right? There is color noise. So color noise basically generally, if you pass the W, okay, and through a certain kind of a channel, okay, then the signal out of that channel, let's say if I use H at here, okay, most probably it's going to become a colored noise. Okay, so the channel here maybe it's a filter basically. Okay, it's a low pass filter or high pass filter. Right? It's like you have a spectrum which is flat. Then you pass that to a low pass filter. Basically, the high frequency part of the spectrum is going to be gone, right? Then just the low pass. So that means the output here is going to be a colored one here. Okay. There are a couple of very important color noise. You can go and check. You can go and do a little research on your own. So, for example, there is so-called pink noise, okay, and there's so-called brown noise. Okay, yeah. Okay, so you can check this out, okay, and at your own pace there. Is that good? Okay. So now let's take a look at a couple of properties of this white noise. Okay. Okay, of this white noise here. First of all, we're dealing with the white noise. Okay, and let's take a look at this white noise W of n and here. Okay. And first of all, this mu W of n, okay, will be. We'll use W bar here, not the vector. Will be what? 0, right? Will be 0. So when you write this one here, remember, now this will happen. Mu Wn, meaning what's the mean value at 0? What's the mean value of 1? What's the mean value of 2? You know, basically like what I showed you at here. Okay, I showed you here. Okay, that's the mean value of this. Okay. And what will be the autocovariance? Okay, what will be the autocovariance set here? So autocovariance you're looking at is a CW, okay, So basically what you're looking at is this. So autocovariant is this. So here is the W of n. Okay, here's the W of n. Okay, then you look at it. Okay, so let's say a may be 1 or 2, right? Or 1 or 2, any numbers you want. Then you look at the relationship between Wn and W of k. So here's this instance here. Here's this instance 1 here, right? And then you look at maybe a W of 4 here. Okay, look at the 4. So basically you look at this sequence and this sequence here. And the difference between these two is that k is what? 1 for that's 3, right? That's 3. Okay. So essentially, what's the covariance? How are they connected? What's the relationship between these two sequences here? Okay. Yeah. So that's what happens here. So the covariance basically we're looking at is a C. Right? We use COV, right? Like this indicates this autocovariance, like this, right? Yeah. So basically, because they're all the same thing, because they're all W here, you can sometimes you call it CWW or just a CW, doesn't matter, okay? Because they're same out of the same random process, right? Out of the same random process. Stochastic process. So from our previous just the review there, okay? So what we're gonna get? We're actually gonna get this thing here. Now remember, this is a y naught, and all the mean value are 0, and also the sigma, right, is the y naught is 0 and sigma square. Let's call it W maybe. Okay, yeah, sigma square. So certain kind of a variance, right? Okay. So then the autocovariance based on our previous derivation, what would that be? Diagonal matrix, right? 0, 0 here. This is what? Sigma 1. That's not 1. It's actually just sigma square all the time, right? Sigma square all the time. That make sense? Yeah. Okay. So you can actually prove that this, in this case, because of 0 mean and there's variance here, so the autocovariance is the same, and also all of this here, they are random variables. They're all independent of each other, all independent. Okay. So the autocovariance, you can prove that easily. It's basically the same as the correlation. Okay, the correlation of this autocovariance here. Now, because we're comparing two different, basically random variables separated by the k, so let's just use the k at here, and this RW separated by the k with the k at here, right? So that's, according to the definition, this is what? W of n and W of n plus k, like this, okay, or minus k, no matter. Okay, so the autocovariance and this correlation, autocorrelation, okay, W, is the same thing. Okay, in this white noise process here, right? Yeah. Okay, so I think I've pretty much finished almost everything at here now. Okay. And then we can move on to just a little bit maybe, but there's not much left. So we can move on to the common filter design in the next lecture. Then, I'm not sure, yeah, probably, maybe you can bring your computer here to next time and just see how fast we can go. And if you can finish some, we can start programming. But next Wednesday, bring your computer again, right? Yeah.